So hello everyone. So I'm here as a quantum information scientist, but my training was chemistry. And I stumbled into all of what I'm showing to you today by chemistry. And but the concepts which I'm going to show you are to a good extent the concepts of modern quantum optics. So they apply to atoms, to quantum dots, to ions. And you will see essentially when I talk about a molecule, you might also imagine this could be an atom or another building block in quantum optics where communication may take place here. So when I talk about molecules, I'm talking about them as an optics guy. And an optics guy, like if you deal with molecules, and you in fact are dealing with molecules every day, you have to realize like the molecules I'm talking about are molecules which are like a little bit like these weird molecules which these people have on their kind of on their clothing here. So this is a picture from Tron, and it's an old movie from 1982. And as a special effect, they had UV lighting, and then they kind of painted the kind of actors with these special molecules. So they light up and they shine in a special way. So this was the future, like in the back in the days in the 80s. And but as I said, like you are dealing with these molecules on a daily basis. So what you have are essentially fluorescent markers. So these are kind of normal pens like Sharpies, and they fluoresce. They also exhibit exactly this feature. You shine some blue light in, and you get some red light out. So I also like these molecules, and these molecules look rather like that to me. So this is also a very special molecule. This is a fluorescing molecule, so I shine blue light in, and I get red light out. You will see the features of the red light in a second. So let's understand how these molecules work, and to a good extent, you also understand how quantum dots or atoms work. So first of all, like it's a kindergarten depiction here. We have a ground and we have an excited state, and we can bring the system from the ground to the excited state, for example, in our case with a laser. So there's no kind of real laser pointer here. But let's say essentially I can take a green laser pointer and shine on one of these kind of molecules or on a bunch, like as you normally do, and I get it into the excited state. Luckily, I have some excited state levels up here. So like this is what I see here. And then I can also depict this as a spectrum. So like normally I kind of write down wavelengths. So like high energy is here on the left-hand side. So what I do is I see some kind of excitation spectrum, and I have, due to the fact that these molecules are kind of symmetric, I've shown you the molecule and I show you a picture of the quantum state in a second, they also have vibrational states in the electronic ground state. So I can excite them into the vibrational state of the electronic excited state, and I can also relax them. So, and then red light comes out. So this is the emission spectrum, what I see here. So this is essentially how the light gets out. So these are the vibrational states I was just talking about. They are not necessarily so interesting because they dissipate some heat. There is some internal freedom. So this cycle can go on and on and on. So like if I excite it, it relaxes and emits some light. So you have to realize like these vibrational states are used, like essentially this is what you see of the actors in the former like a picture I've shown you. So essentially, you take a red filter, you see all the redshifted light, and this the UV light where you excite them is suppressed. The interesting point gets when everything is going to brought to kind of cryogenic temperatures. So this is a spectrum. The black spectrum is a spectrum at, let's say, 1 Kelvin. I freeze out all the phonons, all the vibrational states. And these are the zero phonon lines. They exhibit some coherence to the original excitation, or at least they can. So, and these are the phonon rings. I'm not so interested in these, but this is a big problem if you have a quantum network of various emitters. For example, let's talk about the NV center in diamond. They have a large phonon ring. You lose all the coherence. All the information, which is like in the photons, is gone. It's not available anymore as a coherent measure in the NV center. So we are mostly interested in this 0-0 transition. So like if I look at the 0-0 transition, these are super narrow transitions. Like this is the lifetime limited line width of the excited state, of the electronic excited state. This is also like given by the coherence time. Like gamma is 1/tau, like my coherence time. I didn't care if it's T1 or T2, but at this point, maybe there's a factor of 2. But this is on the order, like from the optical coherence, on the order of 10 nanoseconds. It's very fast, even for atoms, even for ions. Like it's very rare that you have ions, very forbidden transition, for example, where you have a much longer coherence time. In the same moment, it means the systems are dark. Highly coherent systems are dark. They don't really emit a lot. So when I talk about fluorescence, and if I talk about these molecules, I always kind of go back to the good old days of single molecule spectroscopy. So this is by Michel Orit. And like these were kind of people who excited like the first time these molecules in a cryostat. So again, like they use these highly coherent and highly stable systems. And this middle friend here, this D-Benz Antantrain, is one of my friends. And they are very nice and they are very coherent. And the interesting point is they work a little bit like atoms. So if you look at the electronic transitions, you realize, okay, there's one HOMO, the highest occupied molecular orbital, and then there's a LUMO, the next orbital, which is empty essentially, and the transition, the optical transition, takes place among them. And there's not much change. So like this redshift, this Stokes shift, is essentially also which ruins to some extent this coherence between them. So here it's very nice. So the Frank-Conan overlap is essentially 1. So these molecules like C30H16, we excite them at 589. We can excite them at 589, and we get some redshifted light out. Or the other option is we excite them at 580. We go into the first electronic and vibrational excited state, and then we get these kind of orange resonant photons out. So they don't blink, they don't bleach, they are in the cryostat. Like I can work with a molecule for half a year if I don't warm up the cryostat. They are available across the entire visible spectrum. So this is something like if you think about like all the molecules, they cover the range like in fluorescence from 400 to 800. This is about the eyesight. Your eye works as a receiver for light in this range. They are extremely bright. And I show you some rates, like now only single photon rates, which are in the millions. So, and these are not million photons, but these are million clicks actually received events. And they are narrow band. As I said, like they are super narrow band given by the lifetime limited line width. And I can detune them by the Stark effect. So they are not really like atoms, which I can detune a little. They are, this is a solid state system, and I can use stress, strain, electric fields to kind of manipulate them. So this is my single photon source. So essentially I have this cryostat here. I kind of freeze everything in. There's a single molecule under a solid immersion lens. So I do homeopathic kind of dilution of my fluorescent marker, which has these special molecules. And then I build a very fancy microscope around there, so to get these photons out. So, and this is a solid immersion lens, so this enhances my collection efficiency very much. And then the sample is like just a liquid at ambient conditions. If I freeze it in, bam, it's a solid. So this is what I see. Like I have one molecule in the focus. So I kind of quickly have a very nice microscope buildup. And I have a focus which is very competitive against normal focus at room temperature, and I get these kind of millions of photons. Now we have about 3 million clicks per second what we can receive. So these are really great slinger photons. And when we talk about rates, like the first measure is how many transfer events do I get? If I use them as kind of secret keys or not, that's a total different story. But here we are talking about, again, like for example, this is a saturation curve. Like this is a typical feature of a single emitter of a quantum dot of an atom. It saturates at some point. And in the same time, I get something which is called anti-bunching. These are single photons. So if there's one photon emitted, there's not another one emitted here. The interesting point is my student, when he worked on that, he fitted it with the least square fit and came to unphysical values. So of course, like this is a G2 function, which shows you how high is the probability to get another photon at the same time. So like the unphysical value is like that it's a negative value. So like the lowest value is kind of clearly 0. So these molecules are very good because like they cannot only just emit light. So like this is kind of a depicted a kind of emission type scheme. So I have a long path filter and I get the red light out. So I have like this frequency scan. I see this typical Lorentzian line. But what I also can do, I can absorb it. I can absorb the light. So I can not only send out the light by a molecule, but I can also receive it. It's interesting because now I have an object which is 1 nanometer large. And I have a focus, which I focus down by my microscope. And I told you it's about 300 nanometer in size from the focus. And it's a little bit weird that I have a small object, which is nanometer sized, and I have a large focus. Like still I get like 12% absorption here. Isn't it weird? So okay, let's open the textbook here. So okay, my absorption cross-section, how to receive light by a molecule, is essentially 3 lambda squared over 2 pi. There's no physical parameter in there. It's just the wavelength which is important. Isn't it funny? So like it's not like this is the limit. This is the maximum absorption cross-section, which is set for one emitter at a certain wavelength. Bam, that's it. And this is large. Like this 3 lambda squared over 2 pi is like it's a big thing. Although my molecule is only very, very tiny. My airy disk, like how well I can focus, is also in the same order of magnitude. So let's think what happens here when I just want to suck in light from a photon from one emitter into this molecule. I have to superimpose the fields. And this is exactly what I do here. So it's essentially like E laser plus E molecule absolute squared. And then I get these cross-section, like these extinction terms, like this 2E laser E molecule. Very important. So if you draw the picture in the sense of a kind of Nachrichtentechnik, then you think about it as an antenna. And the antenna, here we have a point dipole, and the absorption or extinction, like let's leave it open, cross-section is way, way larger, of course, than this point dipole. We can do this experiment. I've shown you the experiment. But there's another very nice experiment about kind of 15 years ago. Oh, not for 15, but I think the experiment was 15 years ago. So this is essentially how to play light from one molecule to another. So this is an experiment from Zurich, and I really like this very much. So like, please, like if you think about molecular communication, this is one way. You send essentially, so this is an original depiction, sorry, like this was the quality I was able to find. You see essentially like, here's one molecule essentially with this level scheme which I showed you, and then there's a receiving molecule really far apart. So the experiment looks like this. So you have essentially 2 cryostats, and you can send light photons, single photons from one single photon source to another one. And I think this is remarkable that this is essentially what I call a single photon, single quantum network, if you will. This is very far away from what you've shown, René. But this is really a hard experiment. Like this is one of my rather molecular chemistry approach to one of these problems. Another option would be, okay, let's take 2 molecules and let's make an interference. We've just seen the experiment, the wonderful experiment by Benjamin Rosenfeld in the Weinfurter group about 10 years ago, where they did the loophole-free Bell test, and they interfered 2 photons from 2 distant rubidium atoms to enable this loophole-free Bell test. This is exactly the experiment in Munich. So let's do this. And what you see, if you have 2 molecules up here and you send them to a beam splitter, what you see is this Hong-Uman interference. So I don't really want to explain this in full detail, but it's very interesting to look at it. So if you have these two photons coming into a beam splitter, they essentially go both ways, but you realize if you have a click detection here, you don't have a click detection on the other side. It looks like anti-bunching. I'm tempted not to say two photons go that way or two photons go that way. That's not true, because the photons always, they go to a beam splitter, they go both ways. So they destructively interfere, that's correct. But let's look at this. Okay, we can do this experiment. We can do Hongo model between two molecules. We can also do an experiment very nicely where we rotate such that the molecules are incompatible. This is a so-called Shi-Ali configuration. And then you have to realize if you wait for a joint detection on both arms, then the molecules, just photons on a beam splitter, photons are forming in belt state, like in one of the belt states, an entangled state. So you realize post-selected on the coincidence event right and left, you have this kind of the belt state which comes out here. We can even do something very fancy. We can do a quantum eraser experiment where the photons are not at all compatible on the beam splitter. So they come to the beam splitter in an orthogonal way. But in the moment we detect them both in 45 or 45 and minus 45 degree, we get a certain different outcome. So again, although we realize once more that the interference is not happening at the beam splitter itself, but we realize that the interference happens on the detector side. If we blank out, if we don't know where the photons are coming from. So this is a kind of very special Hongo-Mandel dip and also Hongo-Mandel peak interference where you see this along. So we can, of course, like when we have belts inequality, like belts inequality is measure if these photons are entangled. And of course, we can set them to arbitrary values. Like we can analyze this state in a very nice way. So what we get, like when we set like the relative polarizer angle on both sides, we can essentially do Bell's tomography. So like again, this is relatively straightforward. Here we see, so like this is horizontal, vertical, anti-diagonal, diagonal, horizontal, vertical, anti-diagonal, diagonal, for Alice and Bob's settings. And this is the measurement. This is the theory. You would expect something like 2 square root of 2 as a Bell violation. If we fit these values, just the anti-bunching values, we say, well, what do we have when these two photons are coming at the very same moment, such that we form this Bell state? We get an S, like a Bell state value, about 2.2. And if we just look at the coincidence counts, we also get, like, you realize, like, here we have 23 events which are coincidental coming on our detector. And then we also realize, okay, Bell's inequality is violated. So I've, like René told you this, like, very nice analysis about, like, the experiment in Munich. Here we have an experiment where we send the light of two molecules onto a beam splitter. So does this mean I have later two entangled molecules? So the question is like this is what I've shown you here. And this is the experiment in Munich. So who votes that the molecules are entangled later? Okay, very good. Like maybe, okay. You say they're entangled, okay. Who votes that they are not entangled? Come on, let's say, like, don't you have an opinion here? Just, I think you can shamelessly just, like, it's among us. You can. Here we go. I love it. Okay, this is the key question. Okay, how many degrees of freedom of the molecule do we control? Okay, here we go. Anybody to answer that? Like, I like you asking me a question, which I try to ask the audience. So how many degrees of the molecule can we actually control? Anybody? Anybody molecular physics here? So, okay, I'm in the wrong building. I know. So, but I say, but come on, we were learning about these rubidium atoms, which are going to be entangled after the beam splitter. Like I make a measurement, like Harald Weinfurter, Benjamin Rosenfeld, who built up this experiment. I think Christian Kohlsiefer envisioned everything. You have a joint detection, and then you realize, okay, bam, they are entangled. Okay, so like, there was more vote, like 3 votes were for entanglement. And the rest was against entanglement. I think your question was pretty much on the point. This is very hard. Hey, they are not entangled, like because we do not have the degree of freedom. This, like a molecule, forms a singlet state in the ground state, at least very, very common. So, like essentially, like I don't have a spin state available. It's not like that I have spin up, horizontal, spin down, vertical. No, I have just a photon. And the state which is left over is a singlet state. It's forgotten. So that's pretty bad. So if you think about an atom, yes, you can do this. If you think about an NV center, yes, you can do this. If you think about these molecules, which I've shown you, no. Like it's essentially a little anti-bunched quantum optical emitter. It's very, very hard with quantum dots. I think Atachi Imamoglu in Zurich like did one of the experiments where he was proving like later that the quantum dots are entangled. So there's one way to kind of get molecules. Yeah, go ahead. I don't have any more minutes, but I do this anyway. Yes, like in principle, these are like in the experiment, like from one molecule to the other one molecule, you use them as a detector. That's correct. But on the other hand, you don't have more levels available. You just have the emission of the photon. Yeah. Hey, look, let me walk you through 2 ways where I see that molecules can be a little bit more controlled in such a way that we have more degrees of freedom. So here I show you 2 molecules. One is here, and one is here. This is my laser power, essentially. So if I probe this one, it gets to resonance. If I probe this one, this gets to resonance. If I crank up the power, suddenly I realize that something appears here. So like this is a very interesting state, which is in between these 2 molecules. And it's really like textbook physics. So you have to realize like we have really 2 molecules, molecule 1 and molecule 2. And then we have a kind of coupled system. It's like a diamond system. Essentially, you can you can crank up the power and excite this line here. So you excite both, and you cannot determine which is which. And then you bam, you get the photons out. Like this is a typical cascade way of doing this. This was a random finding, like some 25 years ago. Yes, they are in this case about 9 nanometer apart. Very good point. Like a random finding. So short distance, nanometer, like this is answering your question. So let's look at them. This is the way to do it. If you want to build up a molecular network of molecules who talk to each other, like molecule 1 to molecule 2, you have to ask someone to have this in a beaker and to cook it for you. And this is a little bit nasty, just the name of it scares me. And I would say this is the master of carbon-carbon cross-coupling, Konstantin Amsharov from Halle. Like he can make these molecules. This is a very nice way to kind of get 2 molecules which are very close, nanometers apart, who talk to each other in a coherent fashion, such that you get 2 entangled photons out of there directly. So we were, okay. It's relative to the dipole strength of the molecule, essentially. So, and relative to the relative detuning. I take this minute, but I walk you through like that you get the full picture. We can do some coherent manipulations, like we can do Rabi oscillations. But I want to show you a result of 2025 when we talk about molecules, and when we talk about molecules which communicate. Is important because like this is something where we have a molecule which has a free electron. This is a molecule which was already researched in the 90s by a colleague of yours, Bojančević, and he was doing research on carbines. So these are molecules which have a free electron. So they have a triplet ground state. They are a little bit like an NV center. And since 2025, I'm so sorry that the date is not on here. It's a Chem Archive paper from 2025. You can build up these molecules from the bottom up. It's not like an NV center where you implant one by one of these kind of defect centers into diamond. These are single molecules you can grow from. And you see, for example, like this is a little bit like a triplet ground state where you can play all the spin physics, and it's a very, very important result. So let me sum up pretty quickly here. I try to explain you how molecules work. So they can emit, absorb, and extinct light, so like as single photon sources. And then I try to elaborate a little bit like how molecules communicate. Like, for example, there was the absorption by a laser, which we did and kind of try to optimize. Then there was the absorption from another molecule. We have this optical interaction such that we superimpose two photons on a beam splitter. For example, for this Hongo-Mandel and the Shi-Ali. And then the dipole-dipole coupled molecules. And the last thing was the spin photon interface with carbines. Hey, this was it. I hope that you have a number of questions. So like this is a Rydberg experiment we are pushing forward. If you don't have questions, you're absolutely free to contact me and to join my group. Thank you.
Thanks a lot, Ilja. Are there any questions from the audience?
Go ahead, Jonas. Oh yes, no, yeah. Oh no, this is not exclusive. I think you qualify even better.
I have a very stupid question. How about that?
I love it.
Is there a relation to Rydberg atoms here? Just wondering as far as the absorption properties are concerned.
You can bring molecules to a very high excited state, and you can also perform fully Rydberg spectroscopy on molecules. They don't like it too much in the solid state, though. So if you ask Frederik Merck, like from ETH Zurich, like he's working on molecules in the Rydberg state, of course, you can do all these things, like fancy stuff, but it's very, very hard to have them survive in a solid state environment.
Well, that's too bad. The reason I asked is because you talk about sizes and having something which is nanometers small, not requiring a stupid box to hold them and being a sensor would be very, very nice. But I guess we can't have free lunch. So
yes.
Any further questions? Okay, otherwise, we thank again Dr. Ilja. Thanks a lot.